Okay, we have to take another integral from the UNSW Integration Bee 2024. This was round 2, problem 8. We have the integral from 1 to infinity, arctan of x over x squared dx. Okay, oftentimes when we have arctan integral, we're going to want to use integration by parts on this. But I think what I want to do before I do that is let's actually do a u substitution to try to clean it up a little bit first. So we'll say I'll set u equal to arctan of x. And then we can just rearrange this, taking tan on both sides, we can get a value for x. We can say x is going to equal to tan of u. I'll go ahead and take a derivative on this. So for my dx value, we're going to have, this is just going to become secant squared u du. So we'll go ahead with this substitution. So first, for the upper bound, we have infinity. So arctan at infinity, that's going to be happening at pi over 2. And then for 1, arctan of 1, that's just going to be pi over 4. Now, arctan is just going to be our u value. For dx, we're going to have secant squared u du, and x squared is going to be this squared, so we'll have tan squared of u. But then before I go ahead with this, I think what I want to do is just take these two functions here, secant squared and tan squared, and see if we can clean that up with just a little bit of trigonometry. So we'll come over here. So I can write this, I can bring tangent into the numerator and take the reciprocal. So that's going to give me cotangent squared of u. And then what I'll do is rewrite this in terms of sines and cosines. So secant squared is going to be 1 over cosine squared u. Cotangent squared, this is going to give me cosine squared u over sine squared u. But the cosine squareds are going to cancel, and we're just left with 1 over sine squared u. I can write this as cosecant squared of u. So when we put this back into our integral, we're still going to have this u, but then it's going to become u times cosecant squared u du. And now I can look at this as two different things. Now we have u, which is going to be easy to differentiate. Cosecant squared is easy to integrate. So let's use integration by parts. We'll do the di method over here to the right, and I'll just differentiate u, and we'll integrate cosecant squared u. So over here on the left, first we'll differentiate u, we get 1. We'll differentiate one more time, and this is going to become 0. The integral of cosecant squared u, this is just going to be minus cotangent u. And then integrating again, I'm just going to bring the minus down. The integral of cotangent u is going to be just natural log absolute value sine of u. So now the last row, we've got this 0, so we're not going to worry about integrating the last row, but we're going to have our solution here on the diagonals. Now I'm going to go out of order because here minus 1 times minus natural log sine u, that's going to give me here positive natural log absolute value sine of u. And then here we're going to have a minus u cotangent u, and this is all going to be evaluated from pi over 4 to pi over 2. And so now I can evaluate, but I just need some more space. Okay, first let's evaluate now at pi over 2. So natural log sine at pi over 2 is going to be 1. So for this first piece, we just get natural log of 1, but that piece is going away to 0. Then here we're going to have, we'll plug in our u, so this is going to become minus pi over 2. Cotangent at pi over 2, think of it like cosine over sine. Cosine at pi over 2 is 0, so this is actually going to be another 0 right here. So this is 0, so this whole thing is just going away. We'll evaluate this at pi over 4. So sine at pi over 4 is 1 over square root of 2. So we have natural log. I'll drop the absolute value. This is just going to be 1 over square root of 2 minus pi over 4. Cotangent at pi over 4, that's just going to be 1. So now distributing the minus sign in, we're going to have minus times minus is plus. This is going to become pi over 4 minus natural log of square root of 2. I'm going to bring this into the numerator, write it like a minus 1 power. Just because of the natural log, I can use exponent properties. And so doing that, multiplying that minus 1 times this minus 1, we get our final solution of just pi over 4 plus natural log square root of 2. Okay, so there you have it. Pretty straightforward integral from UNSW 2024. Thanks everyone for watching. Have a good day.